In this video, we're going to take a slight diversion and move away from purely organic molecules and take a look at some of the transition metals and the type of chemistry that they do. More specifically, we're going to look at how transition metals form and break bonds with organic molecules in a subfield that's often more specifically referred to as organometallic chemistry. The most important role of transition metals in organic chemistry is to serve as catalysts for forming typically carbon-carbon bonds, although other types of bonds can also be formed with the help of transition metal catalysts. It turns out these types of reactions, so transition metal catalyzed reactions, are incredibly important. I think the vast majority of pharmaceuticals nowadays are produced using this type of chemistry at some step during the synthesis. And the reason is that by using the catalyst, of course, you are reducing the transition energy of some otherwise unfavorable process. But more importantly, the trick is that by using catalysts such as palladium, we're able to very specifically perform a reaction at exactly the location that we want. So, for example, this aryl bromide here is going to only react at this carbon with the alkyne to form a new carbon-carbon bond. So what we're going to do is to just learn a little bit about how all of this works. We're going to go through how to deal with organometallic, what are called complexes, and then look at some of the mechanisms that are really important nowadays in chemistry. I had mentioned this word complex, and I just want to make sure we're all on the same page when it comes to terminology. So here I have the catalyst of the example reaction pulled out. Here. This is the palladium catalyst, and this entire thing is considered the complex. So it's a palladium complex. It's a complicated combination of different things together, I guess, is the reason the name is there. And an important part of a complex is on the metal, we've got a bunch of ligands attached. So one of the important things that we'll learn today is how to deal with these ligands and watch what these ligands do during any sort of a reaction. As part of that, an important concept that we want to learn is that transition metals don't go with the octet rule, they go with an 18 electron rule. And that happens because the transition metals are in the D block, which I've cut out a small piece of here, so they can take on many more electrons. A consequence of that that's really easy to forget is that, this palladium here, it's not a full octet for the palladium. This is actually an 18 electron metal center. So if you look here, palladium is at this bottom right corner of this cutout of the periodic table. So it's got electrons coming from phosphorus, in addition to all these electrons that we aren't drawing on the metal itself. Right? So in theory, there's actually a bunch of lone pairs here that you could think of that we just don't draw. So an important skill when dealing with organometallic chemistry is to be able to count the number of valence electrons in a metal in a given metal complex. The process of counting electrons is not quite as simple as it is for the main group elements, so we'll go through how to do the counting now. The first thing we have to figure out is what the charge of the ligand, or ligands that are attached to the metal, what those charges are. Broadly speaking, we can classify ligands into two different categories. So the first of these would be sigma ligands, and the second would be pi ligands, kind of corresponding to either sigma or pi bonds being formed. There are other types of organometallic ligands, but we are not really dealing with those in this class. So a sigma ligand is going to be either negative or neutral in charge. And I have the three classical examples here. So if I have a metal, and it's attached like this to what looks like triphenylphosphine here, what I do in my mind, and I look at this, is I take that pair of electrons in that sigma bond, and I pull it over to the other atom, and think about what that looks like as a separate molecule. So it's as if the ligand was no longer attached to the metal. So this is what I think about, and I look at this and I see that the phosphorus is a neutral atom here, and so that means that this as a ligand is a neutral ligand. And furthermore, because there were two electrons in that bond there, this is a 2-electron neutral ligand. So in contrast, if I take a metal chloride bond here, and I do that exact same thing where I'm thinking of that pair of electrons being instead only belonging to the chlorine, what I'll see then is that I create a ligand that is negatively charged, so chloride, and that then tells me this is a negative 2-electron ligand. A slightly confusing case that comes up is when you have a very common ligand, which is carbon monoxide. So this is very important and common in organometallic chemistry. If you go and move these electrons over to the carbon to try to do your formal charge determination, what you see is your carbon is formal negative, but the overall ligand here is neutral, and so carbon monoxide is a neutral 2-electron ligand. This is the one that has the most confusion around it, so that's why this example is here. So again, your sigma ligands are going to be either negative or neutral, and the way I think about that is to take the electrons shared between the metal and the ligand and then assign those electrons to being only on the ligand and then look at the formal charge there. The second type of ligand that we'll look at are pi ligands, and pi ligands are a little bit more complicated. They can be either negative, neutral, or positive, and they can also be more than 2 electrons. And so it's most instructive to look at examples here. So the first one I have is a classic neutral pi ligand with 2-electron pi ligand. And so the way these are drawn out looks like this. And so what I'm showing you is that the pi bond, the pair of electrons in the pi bond, are associated with the metal. So it's kind of like that pi cloud and the metal are just sitting really close together and forming some sort of a bond. And since that bond is not to a specific atom, the convention is to actually just draw it directly to the middle of the pi bond. So this again is a 2-electron and neutral pi ligand, because this is, if drawn by itself, a neutral molecule. You'll also see ligands that look like this, where the metal is shown as associating with the center of a ring, like this one here. If you haven't seen this notation before, the circle here essentially is indicating aromaticity in the organic ring right here. And so if I look at this, I know it's a 6-membered ring. Then for that to be aromatic, that's got to be a benzene ring, right? And so the implication here is that this metal is associated with all 6 of the carbon atoms at the same time. And this is really possible because transition metals are typically larger in atomic radius. And so there's just much more potential for overlap with all the relevant orbitals that are needed. So anyway, benzene is a common neutral and 6-electron ligand. Another very important ligand is this one right here. So this is cyclopentadienyl. So a 5-membered ring that's aromatic, and so that means there's 2 pi bonds and a negative charge in your kind of isolated drawing of the ligand. So this is a negative and 6-electron ligand. And so we've looked at these pi ligands now where we have isolated pi bond and then aromaticity in that pi ligand. But we can also look at situations where there is delocalization of a pi system, but it's going to be a linear pi system. So a common one that you'll see is this allyl type of system, so a 3-atom delocalization. I've pulled it out here as a allyl anion, so negative ligand, 4 electrons. And in terms of the metal complex here, I'd have the metal kind of associated with all 3 atoms at the same time and taking on that kind of overall 4 electrons in its valence shell. A confusing point here is that this drawing, in theory, could also refer to a positive pi ligand with 2 electrons. So the allyl cation instead. That's a little bit less common, and often people trying to show that will indicate somehow that it's a cation here rather than an anion. So those are the pi ligands, and these are the types of ligands you'll encounter when looking at any transition metal catalyst or any organometallic species. Once you have figured out what the charge is on all of your ligands, then you can go through and figure out the oxidation state of your metal. And so if you recall from probably a general chemistry class, metals come with their oxidation states, right? So we think about having the oxidation state 0, where it has the number of valence electrons that correspond to the column that it's in. So for example, here, again, palladium, we would expect 10 electrons for a neutral or redox state 0 palladium. The way we figure out the oxidation state of the metal in an organometallic complex is to use the total charge of the ligands to get to what the charge is on the metal center. The math is then pretty simple. The oxidation state of your metal is going to be the negative of the total charge of your ligands plus the formal charge of your complex. It's probably most helpful to look at this in an example. So here, taking that palladium This is tetra-triphenylphosphine. So each of these is a neutral ligand, right? So that means the total charge of ligands here is 0. The complex itself has no formal charge on it, so that's also 0. And so that tells me then that my metal oxidation state is also 0. Right? Negative 0 plus 0 equals 0. So that's kind of a simple example. This bottom one here is much more complicated looking. So then I have to go through and figure everything out. So I have 2 chloride ligands on the nickel. That's 2 of those. And then I have this allyl anion, and I'm assuming it's the negatively charged 4-pi ligand. So that gives me 3 total negative charges coming from ligands. My complex itself has apparently a negative charge on it as well. So that's 1 minus there. Plug everything in, I get to the metal oxidation state of being plus 2. So after figuring out the total charge of the ligands and the redox state of the metal, then we're in the position to be able to figure out the total electron count of the metal complex. The way this is done is through a relatively simple equation. And so we're going to take the number of valence electrons of the metal center if it was neutral. So this will make a little sense when I go through the examples. Once we have that number, we'll subtract out the oxidation state, and then we'll add in the number of ligand electrons that are associated with that metal complex. So let's go through these 2 examples. So here is that palladium metal complex. So what I'm going to have is number here, blue 10. So that's that kind of total number of valence electrons that I was thinking of. So I'm getting that by looking at the palladium in the periodic table, seeing it's in this 10th column right here. So if it was just the neutral palladium atom all by itself, there'd be 10 electrons on it. So that's that 10. I determined on the previous slide that there was an oxidation state of 0, and also that each of the triphenylphosphines here was a neutral 2-electron ligand. So 2 times 4 gives me 8. That adds up to 18. So this complex follows the nice 18-electron rule. So indicates this is probably a stable transition metal complex. Another word that will be used to describe this situation is to call the metal coordinatively saturated, meaning again that it just has that 18 electron count. Now let's look at the nickel case. So here, same equation. If I look at nickel, that's just in the same column as palladium. So again, 10 electrons to start off with. I determined an oxidation state of plus 2 previously, so I'm going to subtract that out here, leaving me with really just 8 electrons on the nickel. Added to 8 electrons coming from the ligands, so there are 2 each from the chlorides, and then 4 from this allyl pi system. That overall gets me a total of 16 electrons, and so that tells me that this is a coordinatively unsaturated metal complex. And you can think of this as a metal complex that might be more willing to take on additional electrons, right? So it's a little bit analogous to an electrophile in an organic reaction. So while being able to count those 18 electrons is nice, for the purposes of this class, we're really interested in how these metal complexes work to catalyze reactions. So now what we'll do is to then look at mechanisms. Transition metal catalyzed reactions go through various organometallic reaction intermediates. These can be categorized into 3 types of mechanistic steps, which are then further subcategorized a bit. So the first type of mechanistic step is a change in metal-ligand bonding, where we're thinking about ligands, just like a ligand, as a group that comes on to or off of a metal center. So we can have a process of ligand association, ligand dissociation, or if we kind of in our mechanism need both of those to happen at once, we get what's called transmetallation. So in ligand association, I'm going from a metal with some number of ligands already on it. I'm adding a ligand, so then now I have a metal with 1 extra ligand on it. Right? It's almost really just an addition reaction. Ligand dissociation is the opposite, so I have some number of ligands on my metal. One of them comes off, now I have 1 less ligand on the metal. Transmetallation you can view as either multiple ligand associations and dissociations, or it could be kind of this simultaneous concerted process in which the ligands are swapped. Those two are technically different, but for the purposes of our class, we will treat those as the same thing. Whenever we see ligands swapping between 2 metals, we're just going to call that transmetallation. The second category of mechanistic steps I personally put under kind of what I call sigma bond changes. And there are two processes here that are very important. The first of these is oxidative addition. In this case, what you see is that we get a metal with some number of ligands, and it essentially inserts itself between two atoms here. And so X and Y atoms are bonded together, and I think of this as the metal inserting in between. So now that the metal is the one that's bonded to the X and to the Y. And so the reason I think of this as a sigma bond change is that we're now gaining two new metal ligand bonds, two new metal ligand sigma bonds, and at the same time we're getting a metal oxidation state change of becoming +2. So that's why it's an oxidative addition, because our oxidation state goes up. The opposite process can also happen, and that is called, cleverly, I guess, the reductive elimination. So in that case, we're starting with a metal center with two atoms X and Y on it. The metal is kind of getting out of the way, and then those atoms X and Y are bonding together. So then we are losing two metal ligand bonds. Our metal oxidation state is going down by 2. That's why it's reductive and an elimination. The third type of change that we'll see is in the way that metal centers and pi bonds can undergo some changes. So we should be a little bit careful. These are not the same as metal ligand association or dissociation. So you can have a pi ligand associate and dissociate from a metal. That's not the same as what I'm showing here. What I am showing here are migratory insertion and its opposite, beta elimination, which is also confusing because this is different from the organic version. So let's look at each of these. In a migratory insertion, what I'm seeing is that the R group, which can be really anything that's attached to a metal, so a ligand on the metal, is acting almost like a nucleophile and attacking or adding to one end of a pi bond. And that pi bond, rather than being kind of evenly shared between two carbon atoms and the metal, now becomes a sigma bond. So you can think of it almost like that. So we get to a product like so. In that process, we've reduced the number of ligands on the metal by 1. We've turned the pi ligand into a sigma ligand, and we've created a new, in this case, carbon to R group bond. The metal oxidation state, however, does not change. Because the R group used to be the negatively charged ligand here, now it's the pi bond, what was the pi ligand, that has become the negatively charged ligand. So again, the metal does not change oxidation state. In the opposite, or the reverse process, beta elimination, the organometallic version, what we're getting is that a group that is on a carbon one away from the carbon attached to the metal center is being eliminated. So if you think of an organic E2 reaction, we deprotonate a hydrogen on one atom, the leaving group leaves the other atom. Similar idea here. We are going to think of the metal as like the proton that's getting removed. So we're getting this pi bond formation, and then the R group is leaving, but it's not a great leaving group. And so the only way this is possible is because in the process of leaving, it can form a new bond to the metal. So the metal is in this weird situation where it's both acting like the proton and also as something that's accepting the leaving group at the same time. And that gets you back to a situation where you have a neutral pi ligand and then a negative R ligand. Again, the oxidation state of the metal does not change. So together, those are the more common types of organometallic reaction mechanistic steps. There's a lot more detail in all of those. Again, you would see this in a more advanced class. Now what we'll do is to look at actual reactions and some of their mechanisms. So as I mentioned at the beginning, these types of transition metal catalyzed reactions are incredibly important, and the most important category of these is what are called cross-coupling reactions, in which we are coupling between two separate reaction sites together. The general scheme of these reactions is always going to look like this right here. We're going to have a species that has an X on it here. This is usually some sort of halogen or something else that's a good leaving group. That's going to be the electrophile, and I put that in quotes because it's not strictly electrophilic the same way that it would be in a regular organic reaction. The cross-coupling partner is shown here in blue, and this would be the quote-unquote nucleophile. Again, not quite the same thing as a regular organic nucleophile. And as the product of the reaction, what you're going to do is to bring the R group attached to the leaving group and the R group attached to the metal and put a bond between them. The way that these transition metal catalyzed reactions are kind of classified is to look at the metal containing side of the reactant pair and to notice that there's all sorts of different metals that can show up here. So really M can be things like magnesium, zinc, copper, tin, silicon, and many other things. And so we want to be a little bit careful that this metal is not the same as the metal catalyst that's used for the reaction. And so naturally there's a huge number of different possible combinations here. And the way that chemists have decided to categorize these is to name these reactions after their discoverer and to categorize these reactions by the metal in the nucleophilic reacting partner here. So each one of these M's is associated with a different person who discovered that reaction. We're going to go through 4 of these, what are called catalytic cycles. These are very complicated. This is not something I'm expecting you to memorize, but it's something that I think you should be able to interpret if presented to you. So the first type of reaction we'll look at is the Stille reaction, and the Stille reaction always couples an organotin compound with some sort of an electrophile. So here's our organotin, here's the reacting partner, here's the metal catalyst. So when we're thinking about mechanisms, we're always going to start off with the catalyst here, and for palladium catalyzed reactions, all of the reactions we'll look at today are palladium catalyzed, we're always going to start from the neutral palladium. And so what you sometimes will see is a reaction which does not have a neutral palladium in it. And in those cases, what's happening is something extra at the beginning here that turns that palladium into a neutral palladium species. So we're always going to be here in our catalytic cycle. The first thing that a neutral palladium will do is to perform oxidative addition. And so what we're getting is the palladium goes from being oxidation state 0 to being oxidation state 2 here. And the palladium has inserted itself between the carbon-iodine bond in this example. So this kind of makes sense because I talked about this being electrophilic in some way, and this neutral palladium is giving up electrons by changing oxidation state. And so that's why we're getting this sort of oxidative addition process. The next step that we'll do is a transmetallation because we had one side of our product on the palladium, the other side of our product on the tin. And so we got to swap ligands around to get to what we need, which is both of those on the same metal. So our transmetallation looks like so, where now we essentially swap the iodine with the phenyl group. This makes a byproduct, trimethyl tin iodide. And our next intermediate here, so this palladium complex. That can then do reductive elimination to expel our actual product and regenerate the metal catalyst that can then kind of go around this cycle again. The Stille reaction is an excellent example of essentially the simplest type of metal catalyzed process that we'll see. And we'll always get this pair of oxidative addition and reductive elimination. And in the middle, we're going to do some sort of processes. So in the Stille reaction, you just have a transmetallation. In the next reactions we'll look at, there's a few more things going on. The next reaction we're going to look at is a Suzuki reaction. This couples organoboron molecules with aryl halides. Again, we'll start off at the neutral palladium. Again, we'll do an oxidative addition. Well, that beginning is kind of the same. The difference from the Stille reaction is that very recently only, actually, people have actually figured out that there's a lot more that's going on between the first oxidative addition here and the transmetallations that we need. So for example, here one thing that we see happening is that we get a ligand association and a dissociation where this strong base here, which we need for this reaction, because it's a fairly good nucleophile, ends up doing an association to the palladium and then essentially substituting off a bromide. So you could call this a transmetallation. It's a little weird to say that, I guess, because sodium is not a transition metal. So either of these terms kind of get you to the overall end goal here, but if you're taking an advanced inorganic class, you'll want to be a little bit more specific here. And so this species is very detectable in the reaction mixture, and that is what undergoes transmetallation. And it doesn't quite undergo transmetallation with the original reacting organoboron here, but rather with a species that's formed during the reaction. So the nucleophilic hydroxide that's around is going to add to the electrophilic boron as well. That gets you to this species right here, which can then do a transmetallation where the hydroxide on the palladium swaps out with the phenyl ring. That then gets you to the diaryl palladium, which can undergo reductive elimination, get you to product. A third palladium catalyzed reaction that we'll look at now is the Heck reaction. And this one's a little bit different because it takes alkenes and couples those with an electrophile. The way this works is, again, we'll start off, kind of a broken record here. We're going to do oxidative addition. And because we're dealing with a pi bond now, what we get is a ligand association, where we get a neutral pi ligand on the palladium. At this stage, in terms of what's happening in the reaction, we have to remove a hydrogen here, right? And so that should make you think about acid-base reactions. That's where the triethylamine will come in. But the way that this happens more specifically here is to do a migratory insertion, like so, where the aryl group is going to migrate to one end of the pi bond. We were thinking about the migrating group as being somewhat nucleophilic, and so it makes sense to add it to the terminal end here because that's more partial positive because of the carbonyl. And then that leaves this carbon right here to be bonding to the palladium. So if you're looking at this intermediate and comparing it to the product, what you might see is that we need to do what looks like an elimination to make the pi bond here. This, in an organic sense, you would think of as deprotonating, kicking out a leaving group, right? But that's not how it works here. What we then do is that beta elimination instead, so the organometallic version, where the hydride, so not H+, but rather H-, is going to migrate onto the palladium, and that's going to kick out the pair of electrons here, making the pi bond. So it's a little weird because it's like the hydride is the leaving group. That then gets you the ligand. Some people might argue that this is still associated with the palladium and you should show this as a separate ligand dissociation step. That's fine too. Either way, you're going to get to product being formed. And this palladium complex and that palladium complex can be reductively eliminated to make HBr, which should immediately protonate your base. Right? So this might even happen simultaneously. Triethylamine deprotonating the hydrogen, bromine leaving, getting you the salt. The final reaction we'll look at is the Sonoga-Shira reaction, and this takes alkynes and couples those with the electrophile. This reaction is a little bit different because it has both a palladium catalyst and a copper catalyst, and so there are two separate catalytic cycles going on at the same time, and they're going to intersect, which makes sense if they're somehow interacting together. So I'm actually going to start off at the copper side here, just walk you through what's going on. So we're going to get copper, which is pretty notorious for forming pi complexes. So this will form a pi complex with the alkyne through ligand association. And it turns out by doing this, we're pulling some electron density out of the alkyne, and that makes the hydrogen here a little bit acidic, and apparently acidic enough to do a deprotonation using triethylamine, which I should show with a positive charge in the product. The deprotonated alkyne is then going to be negatively charged at carbon, and so kind of simultaneously what we see is that we form, instead of a neutral pi ligand, we move over to having the negative sigma ligand. And so this is our actual coupling partner during the reaction. And so the left side of the reaction is just like the Stille reaction, where we did an oxidative addition to the neutral palladium. That will then transmetallate with our organocuprate here. And that gets us to this intermediate, which can then reductively eliminate back to catalyst and product. So I know this was a very different topic from what we've been looking at before in organic reactions, but it's really hard to avoid talking about transition metal catalyzed reactions in the world of organic chemistry because they are just so ubiquitous and so important, and they can do so many things that our regular organic reactions can't. And so again, I think what we want to take away from this video is just having understanding that there are catalytic cycles and that there are types of mechanistic steps that take place in those cycles, and that if you're not sure how to determine the type of mechanistic step that's going on, you can use 18 electron counting to go back and figure out what the changes in oxidation states are in the mechanistic steps, and that can help guide you a little bit in terms of determining what type of mechanistic step is happening.